All right, today we start chapter 14 on sound. It should actually be a rather fun chapter, especially the experiment that we do, the speed of sound in air. Let's get to the PowerPoint. It's a little bit slow. If you recall, we discussed longitudinal waves and transverse waves, and I even put a little demo video on the chapter 13 modules. Sound waves are longitudinal waves. In this topic, we will explore different characteristics of sound waves, like how they're produced, what they are, and how they travel through matter. We will also look at how sound waves interfere with each other. There we go. Musical instruments produce sounds in many different ways. A clarinet, for example, has a vibrating reed. A drum produces sound through the vibrations of the drum head. A piano strings vibrate. And for a singer, it is the vocal cords that vibrate and produce sound. There's an instrument that produces sounds without making any physical contact with, and that is the theremin. It looks like theremin, Theremin. Look it up on either YouTube or Wikipedia. Extra points, you can give me a little write-up about what it is and how it's been used in the past. Theremin, Theremin. Okay. Musical instruments produce sounds in many different. I was already there. Sorry about that. Here we see a tuning fork, and this is how we'll be producing sounds in the lab experiment. Sound waves are longitudinal waves traveling through a medium like air, for example. Let's look at a tuning fork, which is a common device for producing pure musical tones. A tuning fork consists of two metal prongs or tines that vibrate when struck. The vibration disturbs the air near them, as shown in the figures, although the amplitude of the vibration is very exaggerated. When a tine swings to the right, as in the figure on the left, the air molecules in front of the tine are forced closer together than normal. They're forced closer together than normal. This is a region of high molecular density and high air pressure, is called a compression. This compression moves away from the fork like a ripple on a pond. When the tine swings to the left, as you can see in the figure on the right, the molecules in the air to the right of the tine spread apart. And so the density and air pressure in this region are lower than normal. Regions of reduced density are called rarefactions. So sound is the traveling of compression and rarefactions of air molecules that reach our ears. Okay. As the tuning fork continues to vibrate, a succession of compressions and rarefactions forms and spreads out from the tuning fork. The air pattern is a bit like what is shown in the top figure here. We can use a sinusoidal curve to represent a sound wave, as you can see in the bottom figure. Notice that there are crests in the sinusoidal wave at the points where the sound wave has compressions and troughs where the sound wave has rarefactions. The compressions and rarefactions of the sound waves are superposed on the random thermal motion of the atoms and molecules of the air. Now we've seen that the motion of air molecules near a vibrating object is back and forth between regions of compression and rarefaction. This motion is characteristic of a longitudinal wave. The motion of the elements of the medium in a longitudinal sound wave is back and forth along the direction in which the wave travels. On the other hand, in a transverse wave, the vibrations of the elements of the medium are at right angles to the direction of travel of the wave. Okay, next section is 14.2.